Hi everyone. So this is uh, NPTEL course under uh, Dr. Dilip Patil, and this is the course name Introduction to Algebraic Geometry and Commutative Algebra, and this is the 8th lecture, Local Global Principle. So first, let us go through some preliminaries. A property of modules is called local if the following holds. And A module V has this property that it is called local if and only if all the localizations Vp, where P is your prime ideal, that is P belongs to spec A, considered as AP modules have this property. Uh, uh, have this property that yeah, and also one can also use the corresponding definition for rings, ring homomorphisms and module homomorphisms. So now let us begin with our first question that says, let V be an A module over a commutative ring A, then the following statements are equivalent. That says that V equals to 0 and Vp is 0 for all P of spec A, and Vm, that is where M is your maximal ideal, that is spec max of A, Vm is 0 for all M belongs to spec max A. So you have to prove that all of those three statements are equivalent. Okay, so uh, let us start with our first proof. So one thing is clear that if V is 0, then Vp is 0 for every prime ideal, because the elements there are of the form uh, A by small p, where your small p coming from P. And also another statement is obvious, is that 2 implies 3, that says that uh, if Vp is 0, then Vm is 0, because all the maximal ideals are also prime ideals. So only thing left to prove is that if Vm is 0 for all M belongs to spec max A, then V is 0. Now let us start proving this. Assume that V is non-zero, then there exists small x from V such that x is non-zero. Now if you consider the annihilator of the element, that is small a, this set consists of small a from capital S such that Ax equals to 0, and this is a proper ideal since x is not equals to 0, hence it is contained in some maximal ideal M. Now if you localize at M, you see that x by 1 is non-zero in Vm, because if x by 1 would be 0 in Vm, then it should be a dot x equals to 0 for some a in S inverse, for some a in a minus m. But since m contains the annihilator, therefore for every element from a minus m, ax should be non-zero, therefore x by 1 is non-zero. So yeah, what I just said, because localization kills precisely those elements annihilated by some element outside M, but no such element exists since annihilator of x belongs to this maximal ideal. Therefore your Vm is non-zero, contradicting 3, hence V is 0. So therefore you can see that these three statements are equivalent. Now let's move on to our next problem, that says let u and u prime be a sum modules of V, then u equals to u prime, this is equivalent to saying um equals to u prime m for all m belongs to maximal spec of A. Now you shall try this for 5 minutes, then we will start discussing this. Okay, uh, let us try to solve this. So we'll attempt to solve question B, that says that let u and u prime be a sum modules of B. Then we have to show that u equals to u prime is equivalent to saying um equals to em prime for all maximal ideals of A. So if you look into this, if so one direction is trivial, that if u equals to u prime, then um equals to um prime. Now conversely, suppose um equals to u prime m for all maximal ideals m. Now consider the quotient module, that u by u prime. Then you see that wm equals to um by prime, that is 0 uh, for all m. So this implies wm is 0 for all m. So therefore, by the first uh, question, that if vm is 0 for all m, then v is 0. Therefore, w is 0 for therefore w is 0. Hence, e equals to u prime. Now, uh, we go to next problem, that says that let small x comma small y belongs to capital V, then x equals to y equivalent to saying x by 1 equals to y by 1 in Vm for all m belongs to maximal spec of A. So uh, x equals to y, this is equivalent to saying x minus y is 0. Now if you apply part A to the cyclic submodule A into x minus y, then x minus y is 0 if and only if x minus y by 1 is 0 in Vm for all small m. This is because that if you consider this cyclic submodule as V, then V equals to 0, this implies x minus y is 0, and Vm equals to 0, this implies that x minus y by 1 is 0 in Vm for all m. So, and now this is 0 implies this is equivalent to saying that x by 1 equals to y by 1 in Vm for all m. So I hope this is clear. If not, you can ask me a question. Now we go to our next problem, that says let V be an A module and small a belongs to capital A, an ideal. Now suppose Vm equals to 0 for all maximum ideals M containing small a. We have to show that V equals to AV. Again, you should try this for 5 minutes and let me know if you have any doubt regarding this. Okay, so let us start discussing this. uh, yeah, so our V is an A module, and small a is an ideal of capital A, and we are given that Vm is 0 for all maximal ideals containing small a. Then we have to show that V equals to AV. Now again, if you consider the quotient module, uh, W equals to as V mod AV, so you'd see that it is naturally an A mod A module, because if you take any element x plus a from A mod A and multiply it with small v plus AV, then you would see that it would be xv plus AV uh, as an element of V mod AV. Therefore, there is a natural module structure over uh, A mod small a. Now let M be the maximal ideal which contains small a. Then Wm would be V mod AV M, and which is isomorphic to Vm mod A small a capital AM capital Vm. This happens because you know that S inverse of V mod W is isomorphic to S inverse of V mod S inverse W. But what is happening is that you are given Vm equals to 0 for all maximal ideals containing A. So Wm, which is isomorphic to Vm mod something, since Vm is 0, we have Wm is 0. But then for every maximal ideal of A containing small a, the localization W is 0, because the maximal ideals of A mod A are the maximal ideals of A containing small a. So therefore this follows from our proposition 1. And yeah, these maximal ideals correspond exactly to maximal ideals of A mod A. Hence by exercise 8.1.a, that says that this V equals to 0 equivalent to saying Vm is 0 for all m's from spec max A. Therefore W is 0 and V mod AV is 0, and which means V equals to AV. Now let us focus on our next problem, that says let a KVA field I an infinite index set and A equals to k to the power I the product ring. So that for every small p from spec A, the localization AP is a field. Also, uh, every prime ideal of A is maximal. So again, you should try this for some minutes and then we'll start discussing this. Okay, so let's start talking about this. Let K be a field. I has infinite index. Your A is a product ring, and we have to show that for every prime ideal, the localization is a field, and in particular, you have to show that every prime ideal of A is maximal ideal. Now, the step one, we need to know the structure of the product ring. So the ring is the product of is a product of fields. uh, Now for each small I of capital I, let ei denote the idempotent with 1 in the ith component and 0 elsewhere. That is, ei square is equal to ei, and ei dot ej equals to 0 for I not equals to j. And also note that sum of these ei would be 1 comma 1 comma 1, that is 1 in every tuple, and therefore it is for 1 as a, when you consider A as a ring. Now if you look at the prime ideals in A, see that let small p be a prime ideal. Now for each I, since ei square equals to ei, we have that ei dot 1 minus ei is 0 and p is a prime. So this belongs to, I mean 0 belongs to p, so this product ei dot 1 minus ei belongs to p. So therefore, since p is a prime, either of them should be in p, that is ei belongs to p or 1 minus ei belongs to p. But 1 minus ei equals the sum of all ej with j does not equal to I. And if two different idempotents ei and ej were not in p, then both 1 minus ei and 1 minus ej would lie in p from this, and hence their difference ej minus ei would lie in p, forcing ei belongs to p. So this gives us a contradiction. Thus there exists exactly one index I0 such that ei0 does not belongs to p, and for all I does not which does not equal to I0, ei belongs to p. Now it follows that p is the set of all tuples from k to the power I such that ai0 equals to 0. Hence a mod p is isomorphic to k. That is because all the other elements is equal to a, and so this will become something a to the power I by a to the power I minus a single element. That is so when you mod them out, you will get only a single tuple, which is k itself. Therefore p is maximal. Now since a mod p is a field, the localization ap is isomorphic to the field, because if you localize at a maximal ideal of finite product, then you can just simply pick it out and mod at each level, and therefore you will really get the only non-trivial tuple, that is k itself. Hence ap is a field. So therefore we have shown that every prime ideal is maximal, and also the localization ap is a field. Now we go to our next problem, that says that let A be a commutative local ring, semi-local ring, that is your maximal spec is finite, there are only finitely many maximal ideals, and so that an A module V is free of rank R if and only if Vm is free of rank R over Am for every maximal ideal M. So it says that if you can see that show that a module is free of rancor, it is equivalent to showing that VM is free of rancor RAM for every maximal ideal M. So in a sense, the problems we are doing addresses this, that a property of module is called local if and only if for all localizations this property hold. So you see that being zero is a local property. Then this yeah uh, this kind of equality is a local property. And here also that the freeness of a module is also a local property. So again you should try this for 5 minutes, then we'll start discussing this. Okay, so let us start focusing on this. Let A be a commutative semi-local ring. This implies that its spec max is finite, and so that an A module V is free of rank R if and only if Vm is free of rank R over Am for every maximal ideal M. Now let us try to prove the forward direction first. That says that if V is free, that is V is isomorphic to some A to the power R, then localization preserves the free modules. That is, localization behaves well under direction. Therefore Vm is isomorphic to A to the power Rm, which is isomorphic to A to the power R suffix m. Thus it is clear that Vm is free of rank R over Am. Now the non-trivial direction is the opposite direction. Assume that for every maximal ideal M or Mi, V suffix Mi is isomorphic to A to the power R Mi. Now let M of A equals to intersection of the all maximal ideals, which is a Jacobson radical. You know that the intersection of all maximal ideals is Jacobson and all prime ideals is radical ideal. Now since A is semi-local, this implies that this intersection is finite, and therefore A mod Ma is isomorphic to intersection of A mod and product of A mod Mi, a finite product of fields. And now consider V bar as V mod MAV. Then V bar is isomorphic to product of V mod MIV, but V mod MIV is isomorphic to VMI mod MI dot AMI dot VMI. Now since VMI is free of rank R, this quotient is a vector space of dimension R over A mod MI. Therefore V bar is isomorphic to product of A mod MI to the power whole R, which is isomorphic to A mod Ma to the power R. Hence V bar is free of rank R over A mod Ma. Yes. Now choose elements V1 to Vr belongs to V, whose images form a basis of V bar. Now by Nakayama's lemma, these elements generate V. Thus we obtain a surjective map A to the power R to V. Localizing at each maximal ideal Mi, this map becomes an isomorphism since both sides are free of rank R. Therefore its kernel localizes at 0 at all maximal ideals. By exercise 8.1 of A, the kernel is 0. Hence V is isomorphic to A to the power R. Thus your V is a module which is free of rank R. Now let us focus on the next problem and the last problem. Let V be an A module of finite presentation over a commutative ring A, so that V is projective if and only if for every maximal ideal the localization Vm is a projective A module. Now for the remark, you can see that being projective is not a local property. However, projective modules are always locally free. So there is a chain that says that free implies projective, projective implies locally free, but not the converse. So you should try this for 5 to 10 minutes, then we'll start. Okay, so let us start solving this. So the question was, uh, let V be an A module of finite presentation over a commutative ring A, so that V is projective if and only if for every maximal ideal spec max A over the localization Vm is a projective A module. Now we will approaching the first direction. If V is projective over A, then it is a direct summand of a free A module. That implies that V A for some index set I, A to the power I is isomorphic to V direct sum W, where W is a submodule of A to the power I. Now localization preserves direct sums and free modules. Hence, A to the power im is isomorphic to V to the Vm plus direct sum Wm. Thus, Vm is a direct summand of a free A module. Hence, projective over Am. Now, we will look into the opposite direction, which is the non-trivial part. Assume that V is of finite presentation and that for every maximal ideal M, Vm is projective over Am. Now use a finite presentation. Since V is of finite presentation, there exists an exact sequence a to the power n to a to the power m to V to 0, where the last map is surjective. It has finitely many elements in the kernel, which produces this a to the power n to a to the power m map. Now let k equals to kernel of phi. Then we have a short exact sequence. 0 goes to k, k goes to a to the power n, a to the power n goes to a to the power m, and a to the power m goes to v, and which goes to 0. Localizing at any maximal ideal m, we obtain that a to the power n m to a to the power m m and vm goes to 0. So therefore, since Vm is projective over Am, the surjection from Am to the power m to Vm splits, and hence the sequence splits locally. That is, Am to the power m is isomorphic to Vm direction Km. Now we will show that this local splitting implies global splitting. That means that for every maximal ideal, if this localization splits, then it splits globally and therefore it will be projective. Now for every maximal ideal m, the short exact sequence 0 to k to a to the power m, a to the power m to v, and v to 0 splits after localization at m, and equivalently the extension class in x1 a v comma k vanishes after localization at every maximal ideal. Since v is of finite presentation, the functor hom v v comma dash commutes with localization, and so does x1 a v comma dash, because x1 is the first derived functor of this hom. Hence the extension class localizes at 0 at all maximal ideals. By exercise 8.1a, that is, we did that an A module is 0 if and only if all its localization at maximal ideals are 0. Therefore, the extension class itself is 0. Thus, the exact sequence splits globally a to the power m isomorphic to v direction k. So therefore, we conclude that V is a direct summand of a free A module, so V is projective. So we finish our class here, and thank you.